some of our very recent preliminary work on 3D-VAR assimilation studies of the Indian region. This is of impact studies using the WR. And then some results of discussions about the impact studies of 3D-VAR assimilation using various non-conventional observations, primarily the satellite observations like quick scan, and then mode is temperature and humidity price, then for the Doppler spectroscopy and radial views, and then finally we will dwell upon the sensitivity study of the effect of 3D-VAR assimilation using different observations of various cases. So most of you must have gone through this. I understand it's not in part 2, skip all of this. So basically we all know that there is never adequate number of observations, and the number of observations is at least two orders less than the total number of degrees of freedom model. So 3D-VAR is indicated earlier. So we need to essentially find out minimize cost function. So I'll just quickly go to the results. Firstly, I'll present some results wherein we use the 3D-VAR assimilation of quick scan for two cases monsoon depressions. So it's formed in 2006. Many of you know that monsoon depressions are basically systems which provide a lot of rain. It's typically formed over the head Bay of Bengal and move westward or northwestward, and they stay for 7 to 10 days to provide a lot of rainfall over the central part of the country, and they can as well reach even parts like Rajasthan. So we've used the WRF model. Then typically in such impact studies, one usually has a baseline or control where no observations are assimilated. And then one has typically a 3D-VAR where that observation, this is quick scan observations are assimilated for a pre-forecast calculation. And then what essentially is done is the quick scan of any of the non-conventional satellite observations is not assimilated, and then the model is done even with 3D-VAR in a pre-forecast mode. So essentially when we compare the results of the base of the control run with the 3D-VAR run, we essentially compare with the duration and the 3D-VAR run is done with the pre-forecast mode. So now many of you know that this monsoon depressions very extensively, and one very important characteristic of these monsoon depressions are their core systems, the lower troposphere, and their warm core systems in the middle troposphere. Now this sort of thing comes out very nicely. If you take the control run, you do have the cold core is not very prominent, but we'll see the next case where the 3D-VAR run then shows part tiger. So what we have done here is we've taken a time average and area average. This is model for the center of the system environment. So essentially the GFS analysis indicates clearly the cold core the lower troposphere and changing over to warm core. So obviously the cold core will go to intensify with height, so you have the relative vorticity profile intensifying, the cyclone vorticity increasing and then decreasing with height. So this is again the area average and the time average points of the relative vorticity field for the GFS analysis control. It's very clear from this figure that the 3D-VAR run very closely follows the GFS analysis, unlike your control. So these are the 24-hour accumulated precipitation for day 1 and day 2. Top panels are your DRM, the bottom panels are your control simulation, and the lower panels are the results of the simulated precipitation for day 1 and day 2 from the 3D-VAR run. So there are difficulties as everyone can notice here. Agreement GFS analysis of controls. So just a quick scan data shows good impact in terms of precipitation, especially for the second iteration. Primarily for day 1, the impact is less for day 2. Now we show some results of 3D-VAR assimilation using the modes, temperature and humidity profiles for again another case of depression over region over the Bay of Bengal. Now these are the sea level pressure patterns. What you see in the left panels, and these are the results of the control simulation. These are the results of 3D-VAR simulation. Now, in the control simulation, it's very clear that the system is not cross land, right? It has cross land over the 3D-VAR, and this result thus is consistent with the observation. Now, if you look at the precipitation again, upper panel gives you the PMO, the middle panel gives you the control, and the bottom panel gives you the 3D-VAR. Again, you can see that the intensity of precipitation is much closer to the actual PMO observations for the 3D-VAR unlike the control. So it's not as if, like, for example, here of course, the secondary forecast, the rainfall pattern is well within it's cross the coast and depressions cross the coast, and so there are some location errors, but as far as the intensity is concerned and the fact that it's much closer to the 3D-VAR clearly convinces that the impact of the mode assimilation has had its desired effect. Now we look at some quantitative measures to highlight the impact of this 3D-VAR assimilation. To this extent, towards the end, we take a small box, some 10 degree by 10 degree blocks, put the depression center. And then we look at the sea level pressure field, and then we find out what is the spatial correlation of the sea level pressure field in both the controller and the 3D-VAR, and this is this analysis. And that's been plotted here. This is spatial correlation of sea level pressure pattern at different times for the 3D-VAR and for the controller. So it's clearly at all times the spatial correlation of the sea level pressure pattern is always higher than the controller. That comes out very nicely. And these are the root mean squared error scale of the sea level pressure field at different times. And again over the same 10 degree by 10 degree box. Again, at all times the RMSE error sea level pressure field is again lower from the 3D-VAR and the frequency. Now these are some quantitative estimates of quantitative estimated precipitation of the entire region or the entire domain for different threshold values. These are the false alarm ratios. Again, if you compare the control and 3D-VAR, the 3D-VAR is unfilled and the control is the field histograms. So you can see that at all the threshold levels, the different values of the rainfall, at all threshold rainfall levels, the false alarms are much less for the 3D-VAR compared to the control. Similarly, the probability of detection is again a measure of how good the forecast. So again, consistently higher for the 3D-VAR. This is the equitable threat score, and this is the bias. So again, they are better for the 3D-VAR. These are root mean squared error of the temperature field at 3 different levels, 850, 500, 200 remember that nobody's temperature and humidity profiles are being simulated. So again, the 3D-VAR has lower RMS error, and this effect comes out much more clearly as we go here than. So these are the RMS error of the dew point temperatures again in the 3 levels, lower, middle, and upper troposphere, and the wind speed. So as we expected, there's not much impact of this reduction of the root mean squared error for the wind speed, because we're primarily assimilating modes, temperature, and humidity profiles. Again, the impact is seen much more clearly in the lower troposphere. Okay. As far as the reduction of dew point temperature errors are concerned due to assimilation of modes, temperature, and humidity. So the results of the simulation indicate that we have a much larger rainfall area, and this is coinciding with the TRMM results in that the system is cross-land, and that's very much manifested in the 3D-VAR results. So we also have a situation where the sea level pressure field has a higher spatial correlation and a lower RMS error as compared to the control one vis-a-vis the analysis. So overall, there's a positive impact of 3D-VAR assimilation due to modes, temperature, and humidity assimilation. So there are some more results, the same ODIS representation. These are basically the time and area average profiles of Q1 by CP and Q2 by CP, which is the apparent heat source and apparent moisture sink. And these are again depicted for the control and the 3D-VAR analysis. Again, these results seem to indicate that the 3D-VAR is much more closer to the analysis. As you can see, the control one is just it's much more closer to the GFS analysis for both apparent heat source and moisture sink. Again, the time and area average profiles the difference of air temperature and relative vorticity. Again, the fact that the lower atmospheric cold is captured well by your control and is depicted in green, while it's not solid green. I'm sorry, it's much well manifested in 3D-VAR as compared to 2D. And again, of course, here of course there's not much difference between 3D-VAR and the control, especially the levels suffer. Again, ETS and bias. Again, ETS for the 3D-VAR is higher and bias is low. Now, we quickly complete some of the results of the 3D-VAR estimation of Doppler lizard and reflected in radial length. We show the results for Cyclone SIDR. Now, we all know the cyclone has a warm core structure. Now, if you do the area average and time average profiles of the air temperature for the central system with the environment, so GFS analysis indicates that you have a warm core. The 3D-VAR is consistently showing this warm core, and the results are much closer to GFS analysis as compared to control. Again, the area average and time average vorticity, relative vorticity profile show better agreement of 3D-VAR and the GFS analysis as compared to control. This is the track of the cyclone SIDR. This is the JTWC, Joint Typhoon Warning Center. That's indicated in red field circles, and the diamonds are the 3D-VAR and the green, and the blue one. Now, so clearly for the last day, so the cyclone is still not crossed land, while it is crossed land for the 3D-VAR. So I don't have results in tabular form which can give you quantitative measures of the pattern errors for different times. But it's very clear that 3D-VAR again does very well. In comparison with the control as far as the track errors forecast. So these are again 24-hour accumulated precipitation of the TR among day 1, day 2 in the comparison with control and the 3D-VAR simulation. The amount of simulated precipitation is much higher and also relatively closer to the TRM observations as compared to the control simulations. Again, the bias false alarm ratio property of detection improved consistently. You have lower false alarms, higher repeatable threat score, higher POD, and lower bias for the 3D-VAR. Again, the space correlation and the RMSE of 9 hectopascal mean fields again shows higher spatial correlation for the 3D-VAR and lower RMSE for the 3D-VAR. So these for the Cyclone SIDR, 3D-VAR clearly reproduce the warm equal layer in 600 cups in 300 hectopascal. The profile of relative humidity, relative vorticity field also consistently matches the GFS analysis. And then the precipitation patterns are also recently done simulated by the model methods with ingestion of the Doppler lizard. Now finally, I'll present a few results of sensitivity study of the effect of 3D-VAR assimilation of observation from various sources. So as I'm indicating here, we have envisaged a set of 8 experiments. In addition to that, we have the control of the basement that goes with those. These are the assimilation experiments. So mode-based assimilation essentially indicates that I'm going to assimilate only the mode is embedded in the file. Then we have the attacks. So these are available at different times. So as soon as they are available, they are being assimilated. And then we have the SSMI. Then we have the IMD, conventional Indian Meteorological Department observations. So G indicates that these are the GPS data available. Then we have the surface again from the GTS, that's Indian Thermal. Then we have the upper end, this is called the upper experiment. So all upper end data from bodies, from atoms, from the conventional GTS, all are being used. And then we have full experiment in which surface, upper end, all possible observations are assimilated. As you can see, M, G, M. So M and G are assimilated here at 0th hour. Then the atoms, SSMI, and the conventional GTS are assimilated here. The results also seem to indicate that these are the experiments which seem to have reasonably better impact. And we will combine the model forecast for each one of those 8 experiments with the 3 rainfall, day 1, day 2, ends up with sea level pressure as well as the lower tropospheric wind speed from inside analysis. These are the mean sea level pressure at different times. Starting time plus 24 plus 48 plus 60 hours of the control run, that's the base of no assimilation run, the top panel. And then we have the atoms run, in which only the atoms temperature humidity profiles are assimilated in the pre-forecast period. Then we have the assimilation of the SSMI run, and only the SSMI observations are assimilated. Then we have the modes, and then we have the remaining 4 observations, the results of the mean sea level pressure. The remaining 4 runs are shown on the next slide. So we have the IMD conventional, we have the surface observation going in, we have only the upper end observation, and we have the full observation. Now to go back and compare the now the interdimensional shows we have a system, which is again the case of the equation, which on fifth at 0 degree essentially cross line and has value of about 990 intervals. Now to see the other results, control is very bad because it has not just passed, it has reached the Gujarat coast. So atoms, of course, the location is fine, but looking at the intensity, it has simulated not a very intense system, still 990 kPa, much higher than the insubordinate. If you look at SSMI, again it's similar to the control. The system has already moved to the west coast, and again modes you have again similar situation. But if you look at the other remaining 4 experiments, the conventional IMD seems to be closer. If you look at the actual values of the sea level pressure on the last day, plus 60 hours forecast, they seem to be a little more intense than the experiment. But again, only surface observations seem to give you a less intense depression, and again, it's very similar to the modes and very similar to the SSMI situations where the system has already reached the west coast. Coming to the upper and the full, unlike IMD, they seem to get not just the position right, they seem to get the intensity also reasonably right as far as the FNL is concerned. Then we have shown the equilibrium threat score and the bias score for different threshold levels and for all these 8 experiments. Now, if you look at the equilibrium threat score, again, IMD and the full experiment where all observations, both conventional and non-conventional observations are being tested, seems to give the best possible impact, and that shows up at all times. If you look at the bias, again, the full experiment and also to some extent clear that the atomic simulation, the upper simulation, the full simulation seems to be better simulation of not only the sea level pressure field, but also in terms of interval stress score and bias score. If you look at the root mean squared of wind speed at 850 hectopascal, typical lower troposphere, 500 hectopascal to the troposphere, and 200 hectopascal to the upper troposphere. Again, the upper and the ATOS and the flow seem to be again performing better. Root mean squared of temperature again, 3 levels, 850, 500, and 400 hectopascal. Again, the full experiment, blue, the ATOS experiment, and the upper experiment, again consistently doing better. Root mean squared error of dew point temperature again 850, 500, and 400 hectopascal. Again, ATOS of full and the upper level seem to be doing better. So, to just sum up, the reduced error values for the field variables temperature, dew point, and wind speed are especially seen in the ATOS, upper, and the full experiments. This is also consistent for the interval threats for the bias curve is concerned. And the model line which incorporated all observations, including conventional, non-conventional, has shown significant reduction in error values for all field variables and also have enhanced interval threat tolerance. So these are acknowledgements. These are a couple of our students.
Any questions? So let's thank the speaker.